Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video on symmetric matrices. So we have come across these before without formally going through what they are. So a matrix A is called symmetric if A is equal to its transpose, or equivalently if each element ij is equal to the element ji, and that's for all i's and j's in the matrix. So that would mean that, the 1, 2 element is the same as the 2, 1 element, and so on. So this matrix on screen A is an example of a symmetric matrix. It is equal to its transpose. So when we're talking about a matrix and its transpose being equal, they must be the same size, and so we're necessarily talking about square matrices. A symmetric matrix has to be a square matrix. So it turns out that symmetric matrices have some very interesting properties. And some of those involve what we've been studying in the immediate 2 lessons before this. It turns out that all symmetric matrices are diagonalizable, but more so they're diagonalizable by orthogonal matrices. So to see why that is and to show this, first we need to understand the concept of generalized eigenvectors. So let's say that I have a matrix A. And of course, A is going to be a square matrix. We're going to look at its eigenvalues and eigenvectors. Now, if A is, say, defective, we know that that means that there is at least one eigenvalue lambda, and it must be repeated, so that its algebraic multiplicity is more than 1, but its algebraic multiplicity exceeds its geometric multiplicity. And we've already learned that when that happens, when the algebraic multiplicity exceeds the geometric multiplicity for an eigenvalue, it means that there won't be enough linearly independent eigenvectors of the matrix to form a basis for Rn, where n is the size of the matrix. A is an n by n matrix. But remember, a vector x was called an eigenvector if A minus lambda I multiplied by x gave the 0 vector. It turns out, though, when a matrix is defective, you can find some other vectors that are, if you like, almost eigenvectors. So those vectors satisfy what we call a generalized eigenvector, which I've just called GE, and each generalized eigenvector has a rank, not to be confused with the rank of a matrix, which is the number of linearly independent columns. A generalized eigenvector of rank K is a vector that satisfies this equation, which is almost the same as the original equation for an eigenvector. In fact, a generalized eigenvector of rank 1 is just a normal eigenvector. So it turns out that if A is an n by n matrix, that means it will have n generalized eigenvectors. So from that, we know that if A is non-defective, all of its n generalized eigenvectors will be normal eigenvectors. But if A is defective, then it will have at least one generalized eigenvector whose rank is more than 1. So remember, the rank, if you like, is the first power of A minus lambda I such that the vector is an eigenvector. So let's now look at a matrix A which is defective, and I'm also going to say that it is symmetric. So because it is defective, it will have at least one generalized eigenvector whose rank is more than 1. So that means we will have some vector which I'll call m, such that A minus lambda I times m does not equal 0, because m is not a normal eigenvector, but A minus lambda I squared times M does equal 0. So because any generalized eigenvector of a higher order is associated with one of order 2, if we can show that this is a contradiction, that this matrix A can't actually have such a vector M, we can show that it is not defective. If we look at that bottom equation here, we can just pre-multiply each side of the equation by M transpose, which would be a row vector. So that would make this a scalar, just a normal number. Whereas here we were talking about the 0 vector, here we're talking about 0 the number. So what we can now do is expand this part of the equation, because squaring is the same as multiplying by itself. And we have this. But because A is symmetric, A minus lambda I will also be symmetric. If I have my symmetric matrix up here and I subtract, let's say, 4 from each element on the diagonal, I'd get -3, -3, and 1. The matrix is still symmetric. So A is symmetric implies that A minus lambda I is symmetric. So I can put a transpose up here, because A minus lambda I transpose is the same as A minus lambda I. You're probably getting sick of me saying A minus lambda I, so let's call that matrix P. So then that expression becomes M transpose times P transpose times PM. So remember, the rule for transposes means we can write this equation like this. What we have here, because A was symmetric, was that PM transpose PM is equal to 0. But PM transpose times PM is just the dot product of PM and itself. So what we found here is that the dot product of PM and itself is equal to 0. So as I said though, PM is a vector, and its dot product with itself is 0. But the only vector orthogonal to itself, the only vector who when you take its dot product with itself is equal to 0, is the 0 vector. So that would mean that PM equals 0. That would mean, because P is A minus lambda I, that would mean that this has to equal 0. But we said it can't equal 0. That is a contradiction. So that means here that if A is symmetric, it can't be defective. It can't have any generalized eigenvectors with rank greater than 1. So what does this prove? It proves that any symmetric matrix is non-defective and therefore diagonalizable. So now we're going to look at why it is diagonalizable by a unitary matrix. So please pause and copy this down if you need. So now we have that A is symmetric. We know it will be similar to a diagonal matrix, which I will call D. So that means A will equal P times D times P inverse for some invertible matrix P. That's what diagonalizing means. But if A is symmetric, it means it's equal to its transpose. So that means its transpose will also equal P times D times P inverse. But if A is equal to PDP inverse, we can just take the transpose of each side. And remember, when you transpose the product of matrices, you have to reverse the order of the products. So we end up with this. Now, of course, D being a diagonal matrix, it must be symmetric itself. All diagonal matrices are symmetric, so I can get rid of that transpose. So now I can equate this equation and this equation. So the only way this equation could hold is if this is equal to this and that is equal to that. So that means that the transpose of P is its inverse, and that of course means the matrix is orthogonal. So the reason that this equation here implies this one here, you can use the cancellation law when you're dealing with invertible matrices, and P most definitely is invertible. It doesn't matter whether or not D is invertible. So note that we say P transpose is equal to P inverse. That's orthogonal when you're dealing with a real matrix, and we're only dealing with real matrices so far. But I want you to note that we are going to look at some complex matrices later, and then we change the word orthogonal to unitary, and it has a slightly different meaning. But for now, we're just dealing with symmetric real matrices A, and they are always diagonalizable, and they're always diagonalizable by an orthogonal matrix. So remember, as I showed in a previous video, this matrix here, P, is the matrix of eigenvectors of the original matrix A. So if P is orthogonal, we saw a few videos ago that means each of its columns is orthogonal to every other column. In other words, the columns of P form an orthonormal basis for Rn. So that means that the eigenvectors of a symmetric matrix are all orthogonal to each other. So these are the properties of symmetric matrices that we'll be looking at in the lesson. So hopefully this video hasn't confused you too much. This has been the luckiest maths teacher in the world. Have a great day.